All right, so I guess it's time to start Indo Ag Science Cafe. Good afternoon or good morning, mostly good afternoon, I guess. I'm Cherry Kubota, sitting in my office at Ohio State University. Welcome to Indoor Ag Science Cafe in February. Again, we usually do the same format, but just to remind, this is recorded. The first part is recorded up to the end of the topical presentation, and then we will be open up for open conversation. The idea is to enhance the communication of between indoor ag professionals and academic, and then we are willing to answer any questions or exchange information. So it's wanted to create very open communication space for everyone who is interested in indoor ag. So today we will have a topical speaker, Tharindu Weeraratne from Autogrow in New Zealand. But before going that, I'd like to do a couple of announcements. Well, first of all, the upcoming cafe series, March, April, May, June are already scheduled. Michigan State University, Chris Peterson, about economics of indoor ag. University of Arizona, Mura Kachira, talking about air circulation, airflow design in the indoor ag system, so more engineering talk. And then May Cafe is going to be Roberto Lopez, again, Michigan State, talking about herbs and some other leafy greens, light quality. So it's those are quite interesting academic talks. And then the June one is from industry again. Nate Story from Plenty is going to share their status and update. So
Sherry, just to add,
yes, Chris.
on my presentation next month, Simone she and I will be sharing the presentation.
Oh, great, wonderful.
So if you'll add a name to the list. There.
Okay, so I will add Simone's name next to yours. That is something we look forward. Thank you.
And I'll give you the more formal title since I just made it up. I'll email it to you after the seminar today.
Okay, great. Thank you. Then I can start advertising that. Great. All right. So and then a couple of conferences. I announced this last month. Greensis is coming up in June. This is a scientific symposium. I think they're doing every other year, every 2 years, once in every 2 years. And then another one is a Vertifarm, first conference focusing on vertical farming in Wageningen University in the Netherlands. And then this is a correct link for the website. Last month, I didn't have this information, but they started putting more information in this website. So that's something you may be interested. So with that, today's topical presenter from Autogrow in New Zealand, Tharindu, is going to talk about importance of application of G by E by M to indoor ag. What else should we consider? So I'm gonna stop share and then let Tharindu share your screen.
Okay.
And then introduce yourself or add your information, and then all yours.
Thank you, Jay.
Okay, looks good.
Okay. Let me take this. So thank you, Cherry, and the organizing committee for giving me this opportunity to speak at Indo Ag Science Cafe. So before we start, I would like to give you a quick introduction of me. I have experience in horticulture lighting industry, and then now I'm working in the control and automation for control environment agriculture with Autogrow. Prior to the industry, I did my graduate studies in molecular signaling in abscisic acid. I specifically worked with a plant cell protein. And prior to that, I've also worked have some experience in plant pathology and post-harvest physiology and technology of cut flowers and cut foliage back in Sri Lanka. So with that, and I've been working with growers, universities, and industry collaborators ever since when I started working in this industry. And it's a very exciting time to be in. And I would like to take this opportunity to work with you guys. And if you have any questions, and I'd love to work with you, collaborate with you in any way, because this is an emerging field and need a lot of collaboration, like Thierry pointed out. With that, I want to discuss a little bit about the importance of application of G times E times M to Indo Ag, and are there anything else that we can consider? So before going into the presentation, I want to give a little bit of introduction of what Autogrow is. So if we go to, this is our website. We have more than 25 years of experience in control and automation. And also we are providing data services to growers to get the maximum benefit out of their growing operations. And I'll go a little bit of detail into what we do at the last section of the presentation. So in this presentation, I will be talking about the topic, a brief overview, and I will take one example of how we use innovative machine vision technology to quantify crop responses. Then conclusions and a bit more information about what we do. So for this presentation, we define Indo agriculture as growing under no sunlight, under light, under electrical or some form of lighting, and the ability to control the environment fully. So this is unique. This is very unique compared to open field agriculture and even to the other forms of protected agriculture. So what's the interaction of G times E times M? So G is referred to genetics or genotype, environment, and management. And the interaction of these three, the product of these three is the phenotype. So phenotype can be the let's say the color of a flower, the purple color of red leaf lettuce, lycopene content of, let's say, tomatoes, or the total sugar content in strawberries. Whatever the outcome, whatever the response that plant produce is the phenotype. It can be from a one gene or an interaction of many genes, and it's very important in cropping, because depending on what cropping system you are using, what environmental conditions you are in, their interaction, understanding their interaction, how they work together is very important. And as you can see in this Venn diagram, so they are tightly coupled, and if you're trying to make them separate, you can there can be a yield loss. If we think the total outcome phenotype is yield, here you can get the maximum or the optimum yield, and understanding all these three makes a lot of sense. So next, why application of these three is important to Indo agriculture. Let's take a look. So in the open field agriculture, because the environment is so much varying, what has been done through extensive breeding efforts to maintain stable phenotypes under these varying environment conditions. What happens during that process is that you have to compromise some of the beneficial traits, and also because of the varying environmental conditions, you have to consider the post-harvest life and how much they have to be kept in post-harvest conditions, like such as how many miles they have to travel before it meets the consumer. So all these things has to be considered to attain a stable phenotype from cycle to cycle, to keep get a good value for the product constantly. When you compare to open field agriculture, Indo agriculture is very different because everything can be controlled to a very finite amount, in very precisely. But at the same time, from these three in the Indo Ag, the plant component is I'm not saying it's heavily understudied. It's we have to work with what we have right now. By saying that, what I'm saying is that we have seeds or the cultivars that are produced optimized for open field that we have to use in Indo agriculture to get the maximum benefit. There might be a compromise we are making, because these genotypes may have been produced to respond to varying environmental conditions, but in this case, it's not. It's very tightly controlled. Therefore, there's a need for us to work with these seed suppliers and breeders to get these specific seeds for Indo agriculture, made for Indo agriculture. If we can have it, we can then control the environment and control the phenotype. Let's say you have a constant environment from day 0 to day 31 for a particular lettuce variety or some other leafy green. Then you can actually engineer. You can produce a certain genotype that can really work with that environmental conditions. On the other hand, you can have a set of genetics in that particular breed that can respond to changing environmental conditions during the life cycle as we change. For an example, some lettuce varieties grown for a certain period, and the final 2 weeks of their life cycle, certain studies and certain industry studies have shown that adding red blue light increases their anthocyanin content, but it only does for certain varieties. But if we can express some of the genes that are useful in this pathway in other lettuce varieties that are not typically expressing, it'll be very useful. And the other thing is, this is now not geographically limited. You can have any seed variety that can be grown in any part of the world because of the growing setup, the Indo agriculture. Considerations for G times E times M is reduce energy consumption. So one of the main energy input is light in Indo agriculture. If we can have crops that are hypersensitive to light, then we can actually we can grow them under low light and have pretty much acceptable yields under low light, and then that actually works nicely into the research, the ROI of the growing operation. In model plants, they have already been done. There are hypersensitive, light hypersensitive phenotypes, genotypes identified, and it's how we work with these suppliers to get these things into crops. Increase yield, few different ways. The yield per square foot basis, if you're looking at that, it can be the increased yield in a plant, or in how the plant structure can be changed so that you can accommodate a classically a wine crop, like a wine crop tomato. How can you grow and how can you make it dwarf and have it grown in 2 levels in a vertical farm setting? One of the other things that I always think about is the higher quality. The consumer, so the consumer always try to willing to pay a premium if the quality is high. Higher quality comes with the term high value crops. Now we all know that it makes sense, and it is easy to make a profit with high value crops if you've grown under for Indo agriculture. But it is also I think it's a way of thinking. Even a tomato variety, you can actually make it at a high value crop just by converting its phenotype, either by adjusting the gene or the environment or the management practices. Once you have, let's say you have a tomato variety that has a significantly high amount of lycopene content and other metabolites, that all of a sudden it becomes a high value crop. And just because we don't have to deal with a lot of post harvest time, how to keep this variety, how to keep the skin texture tight, and all these things, because we don't have to worry about that, because you can grow upstairs and consume pretty much like within 1 mile radius. You can use that, you can actually compromise those traits to make a high value crop. And again, in Indo settings, you can constrain, limit pests and diseases, and that is again a competitive advantage compared to open field agriculture. So it's not only the genetics, because at present, in reality, we have to work with what we have. So it's a matter of changing the environment and the management, and get the maximum quality, maximum outcome from these. Next, I would like to show one of the examples how we use machine vision, artificial intelligence, and machine learning to quantify crop responses. So it's an outcome of all these 3. And in this regard, for an example, you can maintain the E and M stable, and try to understand the function of G, how we change the G and how it responds. So in this study, we used strawberries grown in NFT. This is in our in-house labs, and we use fruit and flower detection using machine vision, and we can also look at plant health status and canopy growth, a bunch of different things. I'm just taking an example of how we did it, and how it can inform a methodology or model of G, E, and M to be optimized for a certain environmental condition. As you can see in this one, what we did was we used the flower and fruit detection as they emerge throughout the life cycle, and that can be used to predict the yield, harvest timing, and quality. What we do is then we tie this back to the genotype and the environmental and management conditions. So everything's going into a database, stored and actually trying. We use that to close the loop for the next cycle of growing the particular variety of strawberry. And because we have such a big database of all these plant data, environmental data, and management data, we can provide so much insights to growers to have to get a better outcome from their crop operation. This is another example of what we do with assessing plant health status. We use machine vision. We use such as chlorophyll reflectance. How much the reflectance depends on how much active and green chlorophyll in the plant. Or we can use the plant thermal state, the leaf thermal state. You can using such as infrared spectrum. In this graph, you'll see that each day how the plant health in this particular instance is the chlorophyll reflectance, the amount, the greenness of the plant, and it changes during the day. Yeah, also you kind of shows the circadian rhythm. When we measure these things, we learn quite a bit of things about the plants, and that's fascinating. Unless you measure, you don't see it. In addition to this, we are also doing crop canopy dynamics, how the canopy is growing. In our initial studies, we are looking at how the crop canopy is expanding in a top view, the visual canopy area, which can be used as an indication for harvest, as an harvest index, because now we know what's the rate the canopy is actually filling, what's the rate the canopy is expanding, and that can be used to determine harvest dates. But then using other techniques, using other type of imagery, you can actually look at the vertical canopy and understand more biophysical phenomena such as leaf area index, and that can be used into modeling. Conclusions, research. What I mean by that is we have to understand the business model, understand who our customers are, what their preferences are. Then we can actually go back to the seed suppliers and find the right seed type, and then use that, and then throughout the growing cycles, however many cycles, you have to measure, and get that insights into to improve your grow operation. With that, I also want to show a little bit about some other work we do. services we do. So in this, what you are seeing here is one of our platforms that we provide customers insights on the environment, on the root zone, and many different aspects, as you can see here. If I show here, it is the compartment, the batching, the day tank, lots of different things. This is not only for indoor agriculture, this is a greenhouse and also protected undercover cropping. So I'll take an example here. It shows the compartment, how the environment is looking like. We try to provide customers insights and use this information to inform their growing. I won't go into detail, but it's fairly extensive. You can even go to things like chill hours, Richardson chill units, growing degree days. We do the analysis for them so that they can use that information to pretty much change the environment or adjust the environment to get the maximum benefit out of their cropping. Similar to that, I just want to show how we monitor the what's going into the plant and what's coming out from the irrigation and fertigation perspective. We measure the EC, pH, how much volume going in, and then we can measure the runoff. What's in the runoff that can give you a lot of idea about what's happening with your system, how the plants are behaving, things like that. One other thing I wanted to show is our lab space, because we are primarily focused on innovation in this space. We have created our own Autogrow lab. So we have software development kits. I can if anybody is interested, I can hook you up with the team who are working with these. But what we are doing is, if you're using our devices or the solutions, then you can control your own solution to work the way you want. And we work through APIs and also the open source hardware platform. We have made an open source hardware, which we call the Open Minder. That's a root zone monitor. Anybody can, the schematics and everything is in the public. So you can make your own hardware. And if you go to our GitHub, there's so much work there in the GitHub space that you can follow, and you can use instructions. So what I'm trying to point out here is it's collaborate. We need to collaborate. We need to talk to each other and always talk to experts, like from universities, and get their insights before we going into much larger operations. Test in a small area always and try to see if it works. With my lighting experience, I know when we work with growers, we always tell them use a small, first do side-by-side studies and see how it works, because different genotypes respond differently to different light spectrum. So it is very important to test, talk to experts, and get their insights to get the maximum benefit out of what we are doing. And with that, I'd like to conclude my presentation.